Today we'll be learning about chi-square statistic. The chi-square statistic is what you use when you want to test a claim of a distribution of a categorical variable. A categorical variable is one that cannot be measured in numerical values. For instance, colors and a package of M&Ms and its distribution is an example of when you would use a chi-square statistic. There are three types of chi-square tests that are used for different purposes. The first one is a chi-square goodness of fit test. You use this to determine whether a hypothesized distribution is true or not. The second test is test for homogeneity. This is used to determine if the distribution of a categorical variable is different from two or more other populations. The last chi-square test is a test of association or independence. This is when you use to determine if there is an association between two variables in a population. When you start testing using the chi-square test, you have a null and alternative hypothesis. The null hypothesis, while other times has been using a p-value or mu for mean, use a statement. The ho states that there's a claim about the distribution of a categorical variable, and the ha states that the variable does not have a desired distribution that you're looking for. For how to conduct a test, we will move on to the next section.
Chi-square distribution problems require three conditions to be met. 1. That the data collected must be from a random sample. 2. That the sample size must be 1/10 less than the population size, meaning that it's independent. And then 3, that there's a large sample size, so that the frequency of the sample must be greater than 5. When these conditions are met, we know that the data is roughly a chi-squared distribution. These distributions are always positive, always right-skewed, and are specified by their degrees of freedom. As shown by the graph, the higher the degrees of freedom of a chi-square distribution, the less skewed it becomes and more like a normal distribution it will be. Finally, the degrees of freedom of a distribution can show several things about the distribution. 1. That the mean is equal to the degrees of freedom, and 2. That the peak or mode of the distribution is at degrees of freedom minus 2. So if the distribution has a degree of freedom of 10, the mean is 10 and the mode/peak is 8.
This is the formula for chi-squared. To calculate chi-squared, you just sum all of the observed minus expected values squared divided by the expected values. You get the sum of all that, and that would be the chi-squared value. We'll use an example where we can use the formula for chi-squared in Acme Toy Company. Acme Toy Company prints baseball cards. The company claims that 30% of the cards are rookies, 60% veterans, and 10% are all-stars. Suppose random sample 100 cards has 50 rookies, 45 veterans, and 5 all-stars. This is consistent with Acme's claim. So we'll use the ICCI method to solve this. And first we want to test the following hypothesis for alpha equals 0.05, with ho being the proportion of rookies, veterans, and all-stars of 30-60 and 10% respectively, and ha being that at least one of the proportions of null hypothesis is false. And then for the conditions, we will conduct the chi-squared goodness of fit test if the random, independent, and sample size conditions are met. And with this, for random, the sampling size was simple random sampling. For independent, you have to multiply by 10. So since there's 100 baseball cards, more than 1,000 baseball cards would theoretically exist. And for the sample size, each level, the categorical variable had expected frequency count of at least 5. And for the actual calculations, to use a goodness of fit test, we need to compute the degrees of freedom, the expected frequency count, and the chi-squared test statistic. And then based on the test statistic and the degrees of freedom, we can determine the p-value. And as you can see, we calculate the degrees of freedom, which is 2. And you calculate the expected counts and also the observed counts. And then you input that into the chi-squared formula. And then you get the chi-squared value of 19.58 for this test, for this particular question. And using the fact that it has 2 degrees of freedom and looking at the chi-squared chart, we can find that the p-value would be 0.00001. So since that's a very small p-value, and it would be less than significant level, and we would reject the null hypothesis. So basically, so that would mean that it's not consistent with Acme's claim.
When you analyze the p-value that is obtained from the calculations and data, you make a decision based on the value that alpha is set at. In most circumstances, alpha will be 0.05. A simple rule of thumb to use when trying to remember how one comes to a conclusion is the saying, when the p-value is low, reject the hoe. By this, we mean that if you had a p-value of 0.03, for example, we would reject the null hypothesis because 0.03 is lower than 0.05. By rejecting the null hypothesis, we are concluding that there is statistically significant evidence to prove whatever the question is posing to be true. If our p-value were to be greater than 0.05, such as 0.09, we would fail to reject the null hypothesis, stating that there is insufficient evidence to conclude whatever the question is asking to hold true. A type 1 error can be remembered by the saying, reject a true hoe. By this, we mean to say that a null hypothesis that actually holds true is mistakenly rejected in the process, resulting in a type 1 error. A type 2 error can be remembered by the saying, failure to reject a false hoe. By this, we mean to say that one did not successfully reject the null hypothesis when it did not hold true. Instead, they accepted the null hypothesis when in actuality the alternative hypothesis was correct. This type of error is known as a type 2 error.